particularly Mars, Venus, and Mercury. So let's start with the closest planet, Mercury. Its radius is about 1/3 of the Earth, and its mass is 1/20 of the Earth. And so gravity is about 1/3 of that on the Earth. So our 180-pound guy, again, would weigh about 60 pounds on the surface of Mercury. There's circular craters that cover the surface, with the largest one being Chloris Basin with a diameter of 1,300 kilometers. And unlike the Moon, where they are formed almost exclusively in Maria, congealed lava flows are found in many of Mercury's old craters and pave a lot of its surface. Since Mercury is so difficult to see, how do we know what the surface is like? Well, there's lots of different methods. One is to look at its albedo, which is the fraction of sunlight that hits the surface and is reflected. A mirror has a 100% albedo, and a black cloth has a 0% albedo. There's some particularly interesting surface features on Mercury. One of them is called a scarp. So a scarp or a cliff forms as Mercury cools and shrinks, like the wrinkling of a dried apple. And we can see here that this crater formed before the scarp formed, since we can still see the cliff in it. So then we can get some timelines by looking at different features and when these different features formed. Another is something that astronomers have dubbed weird terrain. It's a feature directly opposite of the Chloris Basin, and it was probably caused by seismic waves generated by the impact that created that huge crater. It's just this rough, lineated, hilly area that they didn't know what to call it, so they just called it weird. So the hilly and lineated terrain is caused by the shock wave from the impact of the crater. As the impact, and we get surface waves that go around, compressed waves that go through, and they all jumble up here on the opposite side and form this hilly and lineated terrain. Now, Mercury's noon temperature at the equator is about 800 degrees Fahrenheit, and its nighttime temperature is 280 degrees below zero, over 1,000 degrees difference between day and night. These extremes result from Mercury's proximity to the Sun and its lack of atmosphere. Its low mass and proximity to the Sun do not allow Mercury to retain an atmosphere of any significance, and its lack of volcanoes suggests that Mercury never had a significant atmosphere. Only recently we've discovered there were some trace amounts of some gases using spectroscopy, as dominated by sodium. The wavelength of light given in the figure is specific to the light given off by sodium. Other elements in this atmosphere include traces of hydrogen, helium, oxygen, and argon. Helium is a big surprise since it's so light and should easily escape Mercury's gravity field. It is thought that what's really happening is it's constantly being replaced by the solar wind, which we'll discuss later. Now, this atmosphere is not much. It's only about 1/1000th of the Earth's, so even if we stood on the surface, you'd have to have really special instruments to detect that there was any atmosphere. Now, Mercury's poles are always very cold, enough so that small ice caps exist there, perhaps the result of a comet impact that created gaseous water that drifted to the poles and froze out. Mercury has a very high average density, and it suggests that its interior is iron-rich, with only a thin rock or silicate mantle. Now, two possible reasons for a thin silicate surface. Silicates do not condense as easily as iron in the hot inner solar nebula where Mercury formed, and the rocky crust was blasted off by an enormous impact, is another hypothesis. If you look at the cross-section, it's mostly its iron-nickel core, a little bit of a mantle. So again, here we have another large impact hypothesis. Maybe a little bit thicker rocky mantle, something large struck, and as it struck, it essentially destroys the planet. The iron is all liquid, sticks together, the other materials around, so as it comes together, it differentiates again, but most of the rock is gone, leaving only the iron core. Now, Mercury has a very weak magnetic field, probably due to its small molten core, its slow rotation rate, And the field may simply be that of its solid nickel iron core is like a huge permanent magnet, but would be much weaker than the dynamo-created magnet on the Earth. Now Mercury spins very slowly with a sidereal rotation period of 58 and change Earth days, which is exactly 2/3 of its orbital period around the Sun of about 88 days. Consequently, Mercury spins 3 times every 2 trips around the Sun. It's in a locked tidal rotation with the Sun. If I had a hill pointing towards the Sun, as it goes around, 2/3 of the way around, it's going to be pointing in the same direction with respect to the background stars. When it comes back around to the same position in space, it's going to be pointing in the opposite direction. And then as it goes around again, the second time it would be pointing in the second direction. Such a ratio of periods is called a resonance. Mercury's resonance is a result of the Sun's tidal force on Mercury and its very complicated elliptical orbit. The Sun cannot lock Mercury into a synchronous 1-to-1 rotation because of the high eccentricity of Mercury. So because of this, Mercury's solar day is 176 Earth days long. Its day is longer than its year of 88 days. So because of Mercury's slow rotation near perihelion, the Sun will briefly reverse direction in the Hermetian sky. Now, Mercury is in between us and the Sun, and because of that, we will see it transit across the surface of the Sun every few years. On average, there are 13 transits of Mercury each century. This picture shows many pictures taken on a time delay as Mercury goes across the surface of the Sun. Now, Venus, we'll see, has transits that occur in pairs that have a century separating each pair. This picture is of the 2003 transit, and it lasted 5 hours. Only one spacecraft has flown by Mercury, Mariner 10 in 1974-75. Now there's another mission called Messenger that was launched on August 3rd, 2004. It reached Mercury for a flyby in 2008 and went into orbit in 2011. Now why so long? It actually takes much more energy to fly toward the Sun than it does away from it. Now Messenger sent us lots of great images of the surface of Mercury. Here we can see the craters. In fact, in this crater here we can see that little mountain peak that occurs in the middle of it after that happens. We can see craters on top of craters, and you just start to see what the surface of Mercury looks like. Here's some pictures of that weird terrain close up taken by Messenger. Here's another Messenger image where you see this crater have some different material, so you can see some different colors. You can actually see the rays from the ejected material off of this crater. And another crater that you can see the bright rays that go across the other craters around it. Notice again the hill in the center of it.